Data analysis and analytics, and I'll touch on what analytics means shortly, has been a bit of a theme for the day, with people talking about various data that they're working with. This talk is not really about specific types of data. It's really about the philosophy of how to go about interpreting data and how we can have some difficulty sometimes sorting signal from noise, and in fact we can be fooled by randomness. And as a precursor to that, I've put a couple of books up there. Neither of these books have anything to do with geoscience, but I think both books should be read in all undergraduate geoscience courses. They give you a different way of thinking about data. They give you a different way of thinking about the role of chance in your life. And if anyone's involved in exploration, they should have a very solid working understanding of the role of chance and how to maximise your odds of being successful. The book at the bottom, especially the one by Nicholas Taleb, is especially relevant, I think. He's an insufferable egotist if you read the book, but if you put that aside and just concentrate on what he's saying, the content is very good. And in fact, I added the bit in the bracket there in bold after that, so the hidden role of chance in life and markets and your exploration program. It's directly analogous, and I hope some of you go out and read that book. We've already had this mentioned many times today. There's lots of data. We're swimming in it. The title of this talk, Sort the Signal from the Noise. If someone asks you what the answer is when you're dealing with any of these data types, what they're in fact asking you to do is to identify the signal that's buried in amongst all of that raw data. That's our job as geoscientists. To do that, we use the sexy term these days of analytics. Being a grumpy old bastard, I would rather call analytics something like applied maths and statistics, which is what it is, and it's been around for decades in that guise, but now it gets this nice answer. I struggled to actually find a definition of what analytics is, so I resorted to Wiki, and it says things there like the discovery and communication of meaningful patterns in data, and indeed it favours graphical devices to deliver information that's present in the data. So if you think about that, really, as geoscientists, we are all data scientists. We do this every day of the week. It is not new to us, and in fact, we're pretty bloody good at it, and I'm going to come back to that point at the end of the talk. I put that little clip right at the bottom of the slide there because as recently as just this year, the Wiki article itself was struggling to identify any difference between what is analysis and what is analytics, and I think that tells you that the word analytics is just a bit of a sexy word that's kicked around the industry at the moment. So just a little bit about how we go about data analysis in geoscience and indeed in mining. It really follows two paths, and if you have a look at that graphic there, which I think is a really good summary of what we do, typically in exploration we go around the top of that loop. So we start out with data, we visualise it. Indeed, I know a lot of you in the audience use our software IOGAS to visualise your data. I've seen lots of plots shown today that use the software. As an explorationist, we interrogate it there, we visualise it, we make a decision, we find an anomaly, and that's usually the end of the story. But if we push this further, and other things that have been brought up today includes machine learning, a variety of analytics. So if we're working in production, we start out that way, but if we find something that's repeatable or reproducible, then we want to make a model of that so that we can keep applying it to new data as it arrives to give us the predictions that we need. That latter path, the one around the bottom of that diagram, is more normal in production. I've got a simpler way of illustrating this concept. So this is a really simple bivariate data set, just two variables plotted against each other. If you looked at the x and y variables alone on a probability plot, for example, all of the data would just fit together and there would be nothing strange about it at all. There'd be no anomalies present. But by just plotting the two variables against each other, you can see that there's a curved trend line and there's a point that plots off the line, which you can now see because you've looked at two variables at once. Now, as an exploration person, we're interested in the deviant points, or the outliers as we call them. So in exploration, we model the background. We want to model, oops, let's get back. We want to model this so that we can more correctly identify that. But in a production scenario, when you're trying to run a plant, these are typically outliers, so we need systems that reject the dud data points in the data so we can correctly model the background or the process so that we can keep the process under control. So when we're talking about analytics in the mining and exploration industry, we need to keep these distinctions in mind because sometimes we have conversations the end result or what we're trying to do gets confused, and then people get angry with each other because people are talking completely across purposes. Now, a little bit about looking at data. Numbers are just numbers. When we interpret the data, another way of saying that is that we imbue the data with meaning. The interpretation comes from us, not the numbers. The numbers are just the numbers. So we have a critically important role to play in this process. But this creates a problem because we are hardwired to seek patterns in data where there might not be one. And if you read anything about evolutionary biology, and to paraphrase their excellent scientific work, if you're sitting in the savannah in Africa and you think you see a lion, you run. Whereas the group of early humans who sat down to form a committee to work out whether there was a lion there or not got eaten. So that we've evolved with very quick reflexes in our brains to seek patterns and act on them very quickly. Now, that's all good, but it leads sometimes to us seeing patterns where there are none there. And this is where it segues into our industry and us looking at data. So some simple diagram examples of what this means. So there are 3 sequences of 200 coin flips. The result can only be a head or a tail, or 1 or a 0. And all I've done is plotted them as little bars next to each other in sequence. All 3 of those 3 experiments of 200 flips do not look random. If you look at them, you think that looks like a barcode to me, but all of those sequences of information are, in fact, random. Right? But we can't, our brain just almost won't let us believe that that is random information. If I go on and extend this a bit further, and if I take every time I toss a head, I give it a random positive number between 1 and 50, and every time I toss a tail, I give it a random negative number between -1 and -50, and then just accumulate the results, I start to generate some weird patterns. So I can have that pattern, I can simulate the experiment and do it again and get that pattern, I can simulate the experiment again and get that pattern. Now I'm going back to this, we're trying to seek a pattern in data that's actually random. We can't help it. And I think we see this expressed in our industry, and we've already had it said today that there's a problem with the markets and how the markets function. I don't see any difference between a graph like that and that, or that, or that. Technical analysts, technical charters, and that make a lot of money out of this sort of stuff. But I'd argue a lot of the time they're just dealing purely with randomness and charging a lot of people just to put weird lines on graphs and assign a cause to it where there may not be a cause that's actually discernible from the data itself. So, point made. Something a bit closer to home. So we're talking about exploration undercover or superficial exploration techniques, partly in this topic. I can take a line of data like that. It could be a line of soil samples collected up in the Altiplano or on a pampa. We can take that data, we can imbue it with information. We can assign meaning to it. And we might do some things like, there's the data through there, we can calculate a response ratio, we can look at some features like that, which sometimes we associate with faults, rabbit's ears effects either side of an oxidizing sulfide at depth, and convince ourselves we have a drill target in the middle there underneath the line. But of course, I think you know what I'm going to say here, that is actually random data. That is a random number generator. The number's pulled out as a mean of 50 and a standard deviation of 10, and I've just plotted them as a straight line. So this is it. So we are swimming in data. We do try and make sense of it, but we need to be thinking all the time about cause and effect, and is there any valid information there before we go and act? The incorrect decision looking at data like this could cost us a lot of money. You know, we end up going out, sending the drill rigs out to drill a random pattern in some superficial data that we have collected. So this is a published article. So again, it's the contrast involved. So there's my random data, and here's a published article. And next time, when you look at this published article, and I don't mean to pick on these guys, but it is just a good example, they're postulating that they can see an ore deposit at over 300 metres depth through a tertiary sequence which is hosted in Jurassic rocks. After seeing the previous patterns, that might give you pause when you look at that plot about whether it's in fact that it's provided a diagnostic signal of the presence of mineralisation. And here's another one, another published paper. So again, this was published as a successful outcome of an enzyme leach survey to identify blind mineralisation. but I only see randomness on that plot. I don't see any reproducible pattern to me that indicates that there's something being detected underneath where those soil samples were taken. If those problems aren't bad enough, sometimes we actually design a sampling program to almost deliberately to confuse us. So across the top there, I think you're getting with the theme of this talk, again, that's a random sequence of numbers. There is no pattern or information in that data. But all I've done underneath, and this is something we do very regularly, especially in an orientation study, they're some of the most important pieces of work we do in the field, but we try and save money. So we collect samples most tightly spaced over the target we're testing, and then we open up the sample spacing either side of the target. So we look at this and we see all of this activity where the samples are tightly spaced, the lines going up and down, and we ascribe a cause to it and think maybe something's going on because there's something underneath. Every one of those data points have taken off the graph above. There is no signal in that data. It's random, and it looks even worse, or it looks actually like it's got information in it, purely due to the change in sample spacing. Our brain, the visual cortex in our brain looks at that and goes, something's happening because the lines are going up and down. So it confuses us, and we come up with the wrong conclusion. This is an example of something that was published. This was actually a good paper because they concluded that although the sample spacing was variable, it was not seeing the blind mineralisation. But the reason I show this is to make a point that in the literature, 90% of scientific results that are published are positive. And you know damn well that 90% of experiments that are conducted in the world of science are not actually successful. So there's a bias in what we read. And this is a real problem, actually, because especially in exploration, we can often learn more about what didn't work than what did work. So we go to the literature, we read this stuff, we think, that will work. You know, sometimes that has worked because there were 95 other things tried that didn't work, but that one just happened to work at random at that point in time at that location. So we also need to be fairly careful when we're looking at the scientific literature and trying to evaluate the significance of what they're telling us. Skip over a couple of these. So I said the design of the sampling can give us problems, but the design of the sampling can actually help us. So if we're talking about signal to noise, we can set up the sampling so that we can amplify the signal to noise ratio. So this is a fairly old-fashioned concept here. It's just a line of soil samples trying to detect some gold mineralisation. The bulk sample, the purple one, has somewhat of a response over mineralisation, a mild anomaly to background ratio. But we see here, if we take the coarse fraction, we see no signal. But if we take the very fine fraction, we actually amplify the signal a lot. Now this is fairly, 20 or 30 years ago, this is fairly standard exploration geochemistry practice to go out and do an orientation survey, select multiple fractions, and try and optimize the response you can get in your samples to try and amplify your signal to noise ratio. But these days, I don't see enough of this going on in the industry. People aren't working with what they're doing to maximise their chances of success, which is a real problem, I think. Maybe some of it's just been that knowledge has been lost to the industry, or I think the bigger problem is it's not being taught in the universities anymore, and young geoscientists aren't getting mentoring around doing this in the field either. I know a company in Australia that's looking for a principal exploration geochemist, and they rang me up and said, do I know any? I said, well, yeah, but most of them I know are on their last legs anyway. And they don't want to go and work for a company like yours now anyway because they just can't be stuffed doing it anymore. But there's no generation of people coming through that might have 10, 15, 20 years less experience. So to move on, just to make the point here, just rapidly, in fact, Pim, who's speaking later, sent this slide to me. All of the data on the data does not change on these plots, but the line that fits through them does change because it's the fancy of the analyst. Which line are they going to fit to it to explain the trend? But I put it up there because there's one example here which really gets my goat. I don't know how you can translate that into Spanish, but this plot here, so good old Excel, where people plot line profiles and fit a curved line through these data points, is a shocking practice, right? If I ever see it, if a young scientist shows it to me, I just lose my rag over it. It implies that there's been some sort of spatial modelling applied to the data where there hasn't. You should just join the dots with a straight line that goes from dot to dot and be done with it. The other thing about analytics, so often if you're talking to data scientists who don't have a geoscientific background, they think they can solve everything by just with machine learning and just throwing it through something, training algorithms. But sometimes you've got to understand the geological process that has occurred if you can interpret the data properly. And this is an old example, but it's a really good one. So here we've got a stream sediment survey. It's in an arid zone. It's like doing a stream sediment survey out the back here, up in the Andes. Arid climate, but they're stream sediment. So the material in the streams, although they're dry creek beds, they get filled up every decade or so with material. So it's a physical plastic transport of material into the creeks. Now, if you come from a different part of the world, you go in there and you say, I'm going to collect fine fraction. We just saw fine fraction work just a minute ago with gold. I'm going to go out there and get a fine fraction of these stream sediments to try and detect this base metal deposit. I go out, I get nothing. Right? Now, the problem is you don't understand the process. So what's happening is this is an arid environment that the target that you're looking for was weathered. It formed a gossan on the top of it. That gossan has been physically disaggregated and dispersed into the drainage system. Gossan fragments are very resistant to being worn down by mechanical transport. So the signal resides in this case in the coarse fraction, not the fine fraction. So if you look at the coarse fraction, that Ilura was the name of the lead zinc silver deposit, stands out like the proverbial. Like you can find it. But there's one more trick. There's one more thing you need to do. Because they're gossanous fragments, the samples are extremely ferruginous. So the iron also controls the lead in the samples in a background process point of view. So you need to regress the lead against the iron to remove the iron effect in the coarse fraction because it's a plastic transport in the stream sediments, and bang, then you find your target. So it's not just about throwing a process at data to understand it. Sometimes you need to think, right? This is actually a pretty good tool. Here's another example. This one's more complex, but it's an activity diagram which illustrates the hydrothermal reactions that occur in the process of a tin deposit when the alteration goes right through to greisenization. Now, that's pretty hypothetical. When you look at that, you think, yeah, all right, I saw them at university. But if you understand the process, we can take a simple molar element ratio plot, put some nodes and lines on it. And in fact, I think we've seen this diagram already. And we can actually track those chemical reactions on this diagram. So plagioclase to albite, albite to muscovite, muscovite to topaz. So that trajectory on that chemical space diagram is actually a trajectory in alteration space, and you can quantitatively transfer that into 3D in a drill program to identify mineralization. So when I talk analytics, I'm thinking, yes, there is applied maths, but this is really understanding the fundamental process that you're trying to work your way through and applying your brain to the problem. Last couple of slides. Now, one other key thing about the data that we look at in geoscience is it's spatial. Right? So we need to think about spatial variation as well. So if we have a high nugget, then it destroys the information in our data set, a high nugget relative to the sill in the data if we're looking at a variogram. We need a relatively low nugget and a high sill so that we can resolve the spatial variation. Now, case in point, this is now we're looking at data as a grid view. So it could be, I could make up a three-dimensional view, but this is a map view of the data. We look at the data, we image it, we apply colors to it, we sit down and we start drawing lines on it to make an interpretation of the data. And I think you know where this is going, because although it looks great, especially once you start putting lines on a map, it's hard to take lines off a map, right? You put the lines on, but that is all random data, which I've just gridded and imaged. Right? Now, I see this sort of thing actually quite a lot. And one way you can induce that high nugget in just using soil data as an example is inappropriate detection limit, mixing up sample media, so sampling across different soil horizons, the lab stuffing things up. Any number of things can contribute to this problem. But the end result is that something that looks like that, and someone ever shows you a map like that, you just look at it and go, there's no information, there's no signal, just get rid of it, go away. All right. So I'm just going to skip over these last two, so I was nearly at the end anyway, and go to the end. So analytics and data science. I just want to make some points at the end here. So Data science, analytics, interpretation does not belong in your IT department in a company, right? It belongs with you. There's no standard operating environment. It has to be agile, dynamic and scalable. And the most essential element in this sort of work or practice in the industry is the human, right? The human. It's what's between your ears. It's your brain and thinking your way through it. And I really like that quote in bold, which comes from the guy at the bottom there. It relies on an aptitude for the art for observation, mathematics, and logical reasoning. Hard to fit those three characteristics in one human, but if you can find a human that has those three characteristics, then grab them and give them a job as your data scientist, but make sure they've got a geoscience background. And the last point, the very last point, and this is pertinent to exploration, sometimes the most difficult decision you can make when you're looking at the results of your program is that there is no signal, right? It's not there. You can't find it. And walking away is always the hardest decision. Let it go. Right. Thank you.